So looking at the limit of a sequence, it's very similar to finding the limit of a function as x goes to infinity. Here we're taking the limit as n goes to infinity of our sequence, an. So what that means is if the limit as n goes to infinity of an equals L, that means that we can make an close to L by taking n sufficiently large. In other words, as n gets bigger and bigger and bigger, the values of an are getting closer and closer to the value of L. And if the limit exists, then we say that the sequence converges. Otherwise, we say the sequence diverges. So if, for instance, the sequence gets bigger and bigger and bigger and doesn't appear to approach any particular value, right, then we would have that the limit goes to infinity, and so we would say that the sequence diverges in that case. Here's another handy notation is we can just use the arrow notation. We can write an goes to L as n goes to infinity. So in the next few slides, we'll look at some different rules that we can use to evaluate limits, but they're mostly going to be very similar to the rules that we have for evaluating the limit of a function. In this case, we're just rewriting them and establishing how they look for the case when we're taking the limit of a sequence. Notice that for the limit of a sequence, it's always taking the limit as n goes to infinity. So the idea being, we want to see how the terms of the sequence behave as n gets very large. Do they appear to be approaching one particular value, or do they not appear to be getting closer to one particular value? Here's a theorem that says that if the limit as x goes to infinity of the function f of x is equal to L, and that function defines our sequence an, the nth terms formula of our sequence an, when n is an integer, then the limit as n goes to infinity of an is also equal to L. So basically what this theorem says is we can essentially adapt all the rules that we have for dealing with limits of functions into allowing us to deal with limits of sequences. What does it mean to say a sequence limits to infinity? So when we write the limit as n goes to infinity of an is equal to infinity, means that for every positive number m, there is an integer n, such that if n is greater than uppercase N, then an is greater than uppercase M. So essentially it's saying that eventually, I can choose any big number here. Eventually the terms of my sequence will be above that for all n after some cutoff point. Okay, so in this case, if the limit of the terms are going to infinity, then we imagine that they're going to keep getting bigger and bigger and bigger. So at some point they're going to get bigger than some value m, and they'll never get smaller than that. They'll keep getting bigger and bigger and bigger. So if I can do that for any positive value m, then we know our limit would go to infinity. Here are the so-called limit laws that we've had for dealing with limits of functions. Here we're going to adapt them for sequences. So if an and bn are convergent sequences, and c is any constant, then we can take the sum of two sequences an plus bn, and then take the limit of each of the individual terms. I can take the limit as n goes to infinity of an minus bn. I can subtract their individual limits. If I have the limit as n goes to infinity of a constant c multiplied by an, then I can take c out of the limit and multiply that by the limit of an. Of course, if I have just the limit of the constant c, it's just c. When I take the limit of a product, I can take the product of the limits. If I have the limit of a quotient, I can take the quotient of the limits, as long as the denominator doesn't limit to 0. And if I have a positive power, I can take the limit as n goes to infinity of an and then raise it to the power of p. Right, so the limit of the powers is equal to the power of the limits. Notice here that it requires our terms of the sequence to be positive and also the power to be positive to ensure that these powers are well defined. And then one rule that we had before that is sometimes very useful is the squeeze theorem. We established this theorem earlier in the chapter dealing with limits back in Calculus 1. So now we're going to be adapting it to use it for limits as well. So what the squeeze theorem says, if I have three sequences, an, bn, and cn, where the bn term, the term of the sequence of bn, is always between the terms of an and cn sequences. Here for n greater than or equal to n0, so basically just saying at some point this is always going to be true for all n beyond some cutoff n0. If that's the case, where taking the limit of the ones on the end, if these both go to L, then the one in the middle is going to also have to approach L as well. So it's very similar to how we defined the squeeze theorem in the past. Here in this theorem we have, if I take the limit as n goes to infinity of the absolute value of an, and it's equal to 0, then we know that the limit as n goes to infinity of an without the absolute value must also equal to 0. So this is pretty easy to prove, because it relies mostly on this basic fact that if I take the absolute value of a number, that's always going to be greater than or equal to the number without the absolute values, right? And we know that's the case because here the absolute value just makes the number positive. So if an is already positive, then the absolute value gives us the same thing. So then these are equal. On the other hand, if an is a negative value, then taking the absolute value just switches it to a positive value. So then, of course, the positive value is going to be bigger than the negative value. So with that, we can then say that if I take the limit as n goes to infinity of an, this would have to be greater than or equal to the limit as n goes to infinity of an without the absolute value. And therefore here we know if this limit is 0, then this limit must be less than or equal to 0. And notice that I could do the same thing here with negative an. So here, if I know that the absolute value of an is greater than or equal to negative an, again the same argument, The absolute value just makes it positive. So if an is already positive, then this would be the negative version, and so this would be, the positive version would be bigger than the negative version. If an is negative, then this switches it to the opposite value, so negative an would be the same value, so then these would be equal. So here, again, taking the limit as n goes to infinity of either side here, you get 0 is less than or equal to the limit as n goes to infinity, an, but here with the minus sign, I can pull that out. And so dividing the minus sign, we actually get here that 0 is less than or equal to the limit as n goes to infinity of an. So in this case, we've shown two things. We've shown that the limit as n goes to infinity of an has to be either less than or equal to 0, but also greater than or equal to 0. So if both of these things are true, then it must mean that the limit is equal to 0. Okay. So since both of these facts are true, we can essentially argue that if the absolute value goes to 0, then the sequence itself goes to 0. Let's practice with some examples. We've done this limit earlier, but let's remind ourselves the technique that we used. In this case, to manipulate this into a form where I can easily take its limit, what I did was I divided the top and the bottom by n. So it's like I multiplied the top and the bottom by 1 over n. And so that got it into a form where we see here that n divided by n is 1 over, here when I multiply n plus 1 times 1 over n, I get 1 plus 1 over n. And now this 1 over n term here goes to 0. So it's 1 plus 1 over 0 equals 1. Okay. Another thing we should point out is that if the function in the top and the bottom are differentiable, and it's in one of these indeterminate forms 0 over 0 or infinity over infinity, L'Hopital's rule would also apply. So here you might notice that actually L'Hopital's rule applies here. So oftentimes that can be a useful rule to use when you're evaluating limits. Right, in this case, since n over n plus 1 is in the form infinity over infinity. So if you did L'Hopital's rule, notice you would get the same result. How about this sequence? an equals n over the square root of 10 plus n. So is it convergent or divergent? Well, let's see what happens if I were to take the limit as n goes to infinity. In this case, again, it's in this infinity over infinity form. You could certainly use L'Hopital's rule, but let's just try a little algebraic trick. Sort of like we did last time, I'm going to divide the top and the bottom by something that we can use to manipulate. So if I want to divide n inside the parentheses here, or inside the square root here, I'm going to divide the top also by, so it's like I'm really multiplying this by 1 over the square root of n to allow me to do that manipulation. So here if I do n times 1 over the square root of n, there those turn into just the square root of n in the top. Notice now I don't get infinity in the denominator anymore. This goes to 0 plus 1, so I get 1 in the denominator, but the numerator still goes to infinity. So it's infinity. So this is divergent. the limit as n goes to infinity of ln over n. Again, this looks like it's in that infinity over infinity form. Now this one might be a good one to use L'Hopital's rule, because there isn't any algebraic manipulation that really jumps out to me here. So instead, let's see what happens when we apply L'Hopital's rule. Of course, we know that the derivative of ln of n in the numerator is 1 over n. The derivative of n in the denominator is 1. And taking the limit as n goes to infinity of 1 over n is just 0. So there we get the answer very quickly just by using L'Hopital's rule.